Hello, students. So this is the second part of the Monte Carlo simulation. Here, in the previous part, we discussed about how a vacancy concentration uh, can be observed or can be studied with the help of Monte Carlo simulation. In this lecture, we will study how the vacancies which are already existing in a crystal, how they hop, how they move. It means how they move from one place to another. We have considered here a one-dimensional lattice. So these are the atomic sites. So if you consider these as atomic sites, there is a vacancy present here. For example, if we have atoms in a one-dimensional way arranged in this fashion, and there are vacancies created. Like here is a vacancy. Also, there is a vacancy. These vacancies can move from one place to another in the process of hopping. Now, this process can be visualized with the help of the Monte Carlo simulation, which, as previously told, is a technique involving random numbers, a probability distribution. So the process of hopping again is related to the temperature and to the migration energy involved required to hop. So we assign the different constants, and this is in fact is a process of diffusion. This hopping process can be associated with diffusion, where based upon the concentration gradient, the atom moves. So since we don't have a concentration gradient, we will consider here the number of vacancies available. So we have considered the number of vacancies available to be around 1000, and the number of attempts or the sampling of the Monte Carlo simulation has been done with 10,000. The number of atoms, one-dimensional lattice sites, I mean these are the atomic sites which may or may not contain an atom if there is a vacancy. The temperature was again kept at 1000 Kelvin, and these two are the constants, and the migration energy was 1.2 electron volts. Now we calculated the jump probability. That is P jump. P jump is again is numerically calculated by Em by Kt. This is jump probability, and we also kept a probability check. By probability check, we mean that if the if the move atoms has to be less than the jump probability. Now that means if the probability of jump is say 0.2, that means there will be only 200 atoms will move only. So this is known as the probability check. So as you can see, now the position of the atom has also been defined by this. By position of the atom, we mean that the atom is starting from a certain position and it moves based upon the vacancy. Now the moves again is an incremental move, so it is based upon the atoms. So this is a probability check, and the position of the atom moves from -1 to 1. So it means that as it moves to the left, if it is -1, it will move to the left, and if it is +1, it will move to the right. And after all these diffusion probability has been calculated, or attempts have been calculated, what is required is the mean square difference. So this again, the mean square difference has been calculated using this relation, and ultimately when all the values have been obtained, the effective diffusion has been found by this relation. Mean square difference, so this corresponds to MSD x square, it is the mean square difference MSD. This divided by 2 into t, here is the number of steps. So this gives us the probability of diffusion at a certain rate, and which was found to be around 3.2 into 10 to the power minus 7 meters squared per second. Now we have considered here a one-dimensional lattice for simplicity, but for realistic cases, a 2D or the 3D lattice is involved, where the things get a little complicated. So we'll try to discuss 2D and 3D lattice in due course.